All right. So I'm Carsten Munk from the Carsten Foundation, and I'm here to talk to you a bit about how we do verifiable Linux virtual machines on Ethereum. And this is kind of like from a little while back to kind of like fit more in kind of like the more modular narrative. It's a tweet from Hayden from Uniswap, where he talks about that rollups are just chains, and chains are just servers with superpowers like, for example, history, that you can verify it. History is basically using things like sequencers, like for example Espresso or Celestia or other kind of like mediums out there, kind of like, or let's say dunk sharding, something like that. And also that you can go in and kind of like verify the history or kind of like the past, with a little bit like a time machine of these servers in the past, which is where the virtual machines come in, an execution layer. And also, additionally in the modular setup, things like IPFS and Ethereum kind of enables that it is servers that is accessible to everybody. It's servers that can't be shut off because we get the content addressability of IPFS. We get things like Ethereum for the security, and also importantly that these kind of like chains are able to kind of interoperate with other servers, which is what we call bridging, right? And one of the things you kind of realize when you're looking at what servers that are out there at the moment is that basically you find that these millions and millions of servers that exist, they are typically running Linux. Like, it's written using, let's say, existing programming languages, it's written using normal tools and so on. This is kind of like where, and I will talk a little bit about what Cartesi does and kind of like why this is important. So, what we have is the Cartesi machine. It's, let's say, some people call this an LVM. It's an open source RISC-V, and RISC-V is this open source instruction set. It is very documented. It has a bunch of test cases. It's running in real hardware. And what we have done is kind of like implementing a fully deterministic computer or a machine, where basically if you start out in one particular point of state of your machine, you will always end up in the same finalized state of the machine. And where this is kind of interesting is that this is not like some restricted small instruction set like only integers and memory access and those kind of things. It's something that can actually run unmodified Ubuntu for RISC-V. It's not a new project. It's something that's kind of been developed since 2018, something we're still developing on. And at any point of execution history of the machine, basically all the machine state is in the memory. You can kind of like turn it into one big Merkle tree, which means you can kind of like persist the machine at any kind of like particular step and resume execution from it. And what we can do is that we can optimistically prove it. Like you probably have seen this maybe in Optimism Arbitrum. They have this kind of optimistic verification game. You find out kind of like the midpoint where you are agreeing about something, where you're disagreeing about something, kind of like let the underlying blockchain, in this particular case Ethereum, decide on kind of like what's the next step here. One of the tricks we are doing here is that we are compiling this bigger emulator down into a much smaller instruction set, which is the most basic RISC-V instruction set. So when you're looking at our kind of like verification game on chain, it's basically possible, let's say, with anybody with a basic computer science degree to actually tell that this thing is actually implemented correctly in Ethereum. Also, additionally, what we can do is it's also possible to prove this VM in ZK by basically running this virtual machine inside something like RISC-0. One of the nice things about it is that it comes with an API, as in that you can write into the memory, you can get Merkle proofs at any particular part of state, and this is my not very humble opinion here, but basically the ultimate runtime for computation is something that can run pretty much a 64-bit operating system. Now, what do I mean by that it's general purpose? And I think the definition of a general purpose VM today is not like I can run Rust or something like that. It's that you can run actual Doom in an unmodified manner on it. This is basically Doom recompiled into RISC-V with a little bit of, let's say, modification, so we can kind of show the frame buffers kind of while it's running, but we can kind of go in and, let's say, have the non-deterministic input as you're playing the game, having replay, put that into chain, and then being able to kind of like execute the entire execution on chain and kind of decide, let's say, for example, who has the highest high score. Additionally, we can run things like Docker containers pretty much. We can interact with IPFS because the act of getting something content addressed from IPFS is something that's deterministic. We can run Python on it, Node.js, Rust, and basically it's as general purpose as it could be. It's almost like a real computer, but except you can prove it to the blockchain. It is something that's modular. We're using it together with sequences like Express or Celestia, and also one of the things we're working on right now, based on different restaking primitives like EigenLayer and some of the other ones coming out, is that essentially you can send out a sample, let's say your description of your machine, out to the network, get a bunch of samples back from a bunch of operators on something like EigenLayer, and then basically settle that sampling of the computation result into blockchain. And you can basically write your applications for this stuff in anything you want, pretty much. If you want to write in PHP, have a huge economic security on this is how you do it. And this might sound, let's say, difficult and so on, but in fact it's actually very easy. You can go to a documentation, you can quickly get started. You select that you want to have something like a JavaScript application. You start then editing this JavaScript application. It's not something that is like restricted or in some way kind of like significantly modified Node.js. It's actually Node.js compiled into S5 that you are playing with. So anything you want to do in terms of, let's say, node modules and so on, it will actually work. Then you build it, you can run it, you can kind of start interacting with it in terms of kind of like sending transaction input to it, and then you can kind of deploy it onto let's say, any Ethereum-based chain. And at the moment, we are also adding support to kind of like being able to, for example, very easily deploy into existing sequencers or data availability layers like Celestia and Espresso. And that's pretty much it. And if you want to have any more information, you can follow me on Twitter. You can talk to some of us that are here at the conference, read more about Cartesi, or read the deep technical specifics of the Cartesi machine, or join our Discord, which has a very high level of signal. It's not something where people are coming to kind of do airdrop farming or anything. There's actually good developed conversation going on. Okay? And that's pretty much it for my time. Any questions? Otherwise, feel free to join me afterwards. All right, thank you.